And good morning to everyone. And that again was the police for their second day. And what is your cut on that? Roxanne from the police. And we're working with simple interest. That was my hope. And I understand there are some questions. So let's spend some time in that. And I may adjust again depending on how the questions are. But let's spend time in 8.6. So Kim, I know you had a question. We were talking about a problem with yearly compounding. So let's go back to that problem.
That's in your book,
Number
number 27.
27 in the book?
Yes.
Okay. And if I can get the document cam so I can pick up the problem. Okay, the problem states, let's see. I need to get that again so I can, there we go. Let's cut to the document cam. Now we have $400 at 9% compounded annually. And then I believe it says that we want to do this for 3 years. And of course it indicates here calculator to solve. But aside from that, as I go to the board, if you look at our formula in terms of PRT. Now I'm going to try to review a few things here. Interest is the principal multiplied by the rate multiplied by the time. And so the argument is you take your original principal, you find the interest, and you add them together. Now if I just did that for a year, or for 2 years or 3 years, simple interest, no compounding, then the argument is you can take the distributive property and get P times 1 plus RT. Okay. And if you do it for another quarter, the argument is that the amount you get here, and you multiply now by 1 plus RT again, you'll get that new interest, and it keeps adding it in. So this is the amount you'll have at 1 year. Now if I went ahead and said I want 1 year, T would be 1. So this just becomes 1 plus R. So this is the amount at the end of the first year. Well, the amount at the end of the second year, you take what you had the first year, which was P, times 1 plus R, and multiply it by 1 plus R again, because that was your new amount. And so that is at the end of your second year. So at the end of your third year, you take the amount you had in the second year, and multiply it by 1 plus R. And that just keeps adding in the interest to the new principal. Well, the argument is that then the amount in the third year is really just your original principal, 1 plus R to the third power. Now that's an annual rate. Okay. So in terms of the problem we have, where we were to do this for 3 years, that's where the 3 is coming from, the amount I think was $400, correct? And we had it at 9%, and so we get this figure. Now this doesn't turn out to be so bad in terms of a hand calculation in this particular case. But what we usually do is use the y to the x key in the calculator. So we take y to the x, where y is going to be your 1 plus 0.09, and in this case your x is 3. So for this particular problem, it's just putting in 1.09, y to the x, 3 equals, and multiply it by 400. So I'm going to do this. I'm going to put my 1.09, hit the y to the x key, hit the 3, and hit equals, and then multiply by 400. So that's with the calculator we've been talking about. Okay. So if I do that, and I come back center on this, move the book out of the way a little bit, get the calculator down here, clear it out. The key that we want to focus on, and it may help if I do that a little bit. The key is this one, y to the x. Okay. So what I'm going to do is enter the number first. So we come off there for a moment, Ernie. And let's see if I can get that in a little better situation. And what I'm going to do is enter 1.09 and try to get that focused so it reads a little bit better. I can't do it, so I'm out of the light. Well, that didn't work well at all. Now this is the number I put in the calculator, and I can try turning that off. That doesn't particularly help one way or the other. But I'm going to hit the y to the x key. And when I do that, what you see is that I have my 1.09 here. And this little caret means that I'm going to run an exponent, and I'm going to put this 3 in here. So I put the 3 in, and then I hit equals, and I get 1.295, rounding off. So this figure right to here is I need to have that a moment more, 1295. And technically it has what, a 023? Is that a 9 at the end? Thank you. Now I'm going to multiply that by 400. So as I come back center to the calculator, I'm going to multiply now times, so back to the calculator, times 400. And that tells me I have $518. I guess I should put an equal sign here. $518, and it's a .01 what? 6? 116? Okay, so if I look at this number, I'll just rotate. Well, Ernie's going that way. I'll go this way. If I look at this in terms of what the bank's likely to give me, then they probably will give me 518.01, rounding off to the nearest penny. Now, I came across a wrinkle. It's a little bit different than what we did in Math 10. If the bank is advertising a particular annual percentage rate, and they gave you less than what the annual percentage rate would give you, then they may have an accountability to the federal government. And so I'm not at this point as sure as I once felt about this being rounded down. If we were to round off mathematically, we would say 518.01. Now, to put this in context with what we did in the simple interest unit in Math 10, we very seldom did yearly compounding. We did quarterly compounding. So if I look at that same formula, and again I'll just rewrite what we had, because this is going to be important for what we're doing with the problems here. Again, this is still the amount of money you have in the bank at the end of any compounding period. But if I do it in terms of the distributive property, and I look at this now in something like a quarter of a year, quarterly compounding every 3 months, then this T is no longer 1 as it was an annual. If I did it each year, the T was 1. If I do it for a fourth of a year, then T is 1/4. So what we did in quarterly compounding for our Math 10, we said you would have 1 plus R over 4. So we divided by 4. And if you looked at the end of 3 years doing it quarterly, and we said, okay, you're going to have your amount at the end, then instead of doing just 3 up here, we would have 3 times 4, because you did it 4 times a year for 3 years, so this would be 12. Okay, so to that extent, this is sometimes referred to as N, the number of times you compound a year. So this formula, if we generalize it, would be 1 plus R over N, and then you would have your value T times N, or NT, and that becomes your general formula. So this would have been quarterly compounding. If I were to do it semi-annually, then this becomes a 2 and this becomes a 6. If I do it 365 days a year, then it's R over 365, and then I run 365 times 3. And that is essentially what we're going to be doing as we come through these problems. Now, what's interesting, the way we've been talking about it, we could think of this A as a future value. Otherwise, I put a certain amount of money in the bank and just leave it there and let it compound interest, whether it's yearly, quarterly, daily. This is the amount I have in the future. This was its present value when I put it in the bank. So if I look at this formula in terms of what I'm doing here, and I solved for the letter P, then I would take this and say that P is equal to A over 1 plus R over N to the NT, and that's a formula that's talked about for what we say is present value. Now, one of the things I'm trying to work up, and again, sort of getting a feeling for how we're doing with 8-6 and simple interest, the formula for determining how much you pay monthly to amortize a loan involves some of the arithmetic I'm doing here, or algebra, if you will. And so I'm trying, as I answer your question, to sort of get us to the point where we think then of present value. So think of this as present value. And in doing the reading I've been doing and trying to get a presentation that I feel comfortable for you, one particular source said it's working your compound interest in reverse. Otherwise, instead of finding out how much you have at the end of 3 years, start with how much you have at the end of 3 years and ask how much do I have to put in the bank. And so that present value is just working this formula backwards. So you know how much you have at the end. In this case, we said $518. But I could ask the question in a different way. If I wanted $518 in the bank at the end of 3 years, how much do I have to put in the bank today? And that's solving for the present value. And so the argument here is current versus future. You can look at it, here's what I have now, how much will I have in the future? Or you can say, here's what I want in the future, how much do I have to invest right now? So if you say, and again, this assumes there's no inflation involved, but if you say that 20 years from now, 40 years from now, I have to have $1 million in the bank so I can retire, then you can work backwards and say how much money, if I just put a lump sum in today, how much would I need to put in today so I have that $1 million 40 years from now? Future versus present value. And then again, the formula for determining the amount of money you pay each month to pay that off involves some of these same calculations. But I don't want to go into that more than I've done right at the moment. We've used this formula in Math 10. We're just going to rewrite it in 20. And by the way, this is one of the problems you have in this set of problems. You work back and forth. And so the author's actually getting to that without talking about present value. So that's the answer for the first question in this unit, which is from 8.6. Are there other questions that we want to answer? Michael? So number 5, computer homework. Okay, and it was 3,000. APR at 6%.
Compounded semi-annually.
Okay, so compound semi-annually.
For 1 year.
Okay, and you want to know the amount at the end of the year?
Yeah.
Okay, so if I look at what I'm asked to do there, and I take a moment to just look, let's slide over a little bit, Ernie, to pick up this much here. If I look at the amount I want, remember this was based on 4, and so my general formula was right here. So how many times are you compounding semi-annually during the year? 2. So this says I'll take my interest rate, divide it by 2, add it to 1, and T is 1 year, and I'm doing it twice for that year. So I don't think it's, again, if we look at what we're asking about, it's not that you haven't been able to do this in the past with quarterly compounding. What it is something I've been very conscious of this particular semester. The last few semesters, it's been a real challenge to try to cover simple interest so that everybody's feeling comfortable with it. And I'm getting closer this semester than I ever have before. However, to do that, I've focused on one of two things. You compound quarterly or continuously. One of the two. And if I narrow it that far, it works pretty darn well. But now what we're doing is we're saying, well, what happens if you go semi-annually for only 1 year? Or you do annual compounding for 3 years? And that little wrinkle takes what was pretty comfortable, it's just quarterly compounding, and makes it just uncomfortable enough that the questions come up. So what I want to do is take my principal, and you indicated the principal was going to be $3,000. So if I come right below here and just go straight across now, the amount I'm going to have is my $3,000. I'm going to multiply that times the 1 plus, and you had 6%. I'm going to put that over 2, because that's how many times you did it during the year. And 1 year times 2 is just 2. So you're going to take 1.03 and square it and multiply by 3,000. Well, let's see what we get. Let's see what we get as we come back center. Now, as we look at it, we want to go ahead and use the y to the x key. Now, again, 1.03 squaring isn't too bad, but let's do the calculator just to simplify things. So I'm going to put in 1.03. Let's try going to the screen and see if that's, get it out of the glare. 1.03, then I'm hitting the y to the x key, and we said we're going to hit that twice. Otherwise, we're taking it to the second power. I hit the equal sign, and I'm getting a 1.0609. So this part right here is 1.0609, and I'm multiplying that by 3,000. Now, I could do that without too much difficulty just by hand, but let's go back to the calculator now, Ernie. And I'm going to multiply by 3,000, and I'm getting 31827. So the number I'm getting here is 31827. So it appears I have $3,182.70. Is that what you're getting in the calculator as you try it? So again, 1.03, y to the x, 2. I could have just squared it, but I'm going to use the y to the x key. Hit the equal sign, and then multiply by 3,000. And do we get the 3182.7? And is that the answer you were supposed to get?
Well, it kept giving me different figures, and that was the last one that I remember.
Okay. When all else fails, turn off the computer. But does it make sense now?
Yes, it does.
Okay. And again, you're bringing back very clearly to me. It's one thing to talk about these problems focused on quarterly compounding. You do the same thing every time. But now mix it up a little bit, and that's what's had me a little bit nervous about going into formulas for amortization payments. And I'm wanting to make sure we've got all this down before I open the door too wide on the other.
Now, I was using the little blue calculator.
Can't do it with the little blue calculator. Won't do it. You're going to have to, and you're welcome to take out one of the EL 531s and use it over the weekend to do these. That's why I got them. So if you need to do that, that may solve some of the problems. But you aren't going to be able to typically do these problems. Now, this is one you could have. You could have put 1.03 into memory, hit times memory recall, that squares it, then multiply by 3,000, and you'd have the same answer.
I was going 3,000 times 6%.
No, you can't. Because you aren't adding it in. Otherwise, if you take the 3,000 by the 6% divided by 2, because it's for 1/2 the year, then you have an interest value that you have to add back into the 3,000 before you do it a second time. And as much as I've tried to do that with the little four-function calculator, where you basically take your 3,000, put it into memory. Then you multiply times 0.06 divided by 2, add that back into memory. Then times 0.06 divided by 2, add that back into, oh, you have to hit a memory recall first. So memory, so again, 3,000 in memory. Now, multiply your 3,000 times your 0.06 and divide by 2. That's your interest. Add that into the memory with the M plus key. Now, to get your new balance, you have to hit recall memory. Then you multiply that by 0.06 again, divide by 2 equals, add that back in, recall memory, do the same thing. That has not worked well with my class this semester. I've just about given up trying to get them to do that because they get messed up with the M plus, the M minus, the MRC key, and I'm just about to the point saying, okay, we're going to use the EL 531. I've said uncle. It hasn't worked, and I've battled this to my frustration also. But that can be done. Yes?
It was working for me last semester, but...
Well, yeah, you can make it work, but it's one of those things, the operation with the calculator, unless you're doing it all the time, to go back and try to bring that back from the past. All it takes is one failed step. If you didn't do memory recall to get your new balance after you added in the interest, then it doesn't work. And you can't see what's happening. And so, as I say, I have changed my strategy for two reasons. One, the calculators are not working sometimes as well as we'd like. We've had some problems with that, and I can't build on that as well as I can going to the EL 531. So that's the story. So that's our second question. And James, a third question. Now, is this a computer problem? Okay, I'm going to need, I think, well, let's see if I can at least start it here in this corner. Okay, so you have $12,000, and this is a computer problem. What number is it? Number 10, or thereabouts. Okay, and how much do you have? So, but how many dollars? 12,000, and that's our principal? And we're going to do this at 3% for 6 years, quarterly. Okay, I'll just abbreviate quarterly, QRTLY. Okay, Ernie, camera 1 over here, please, and I'm going to go over to the other board, and I'm going to try to do this in two ways. One, let's see if we can do it with a little four-function calculator, since that's the constraint you put yourself under. This one's not bad, okay, with 3 years. You only have to do it 12 times. But it's nonetheless frustrating. You're putting the calculator up already. Okay, we got camera 1 here already? Okay, I'm going to go to the side board.
Remember,
If you miscount, you're also wrong. Okay, but let's see what we've got. Again, back to, thank you, Ernie. We have 12,000. So I'm going to take that 12,000, and I'm going to hit M+. Now, again, the idea is just to put this into memory. So we go to the sideboard and come out just a little bit more than that, if you would, Ernie. Thank you. That puts it in memory. Now, I had 3%, and I'm doing it quarterly. So what you could do is say I'll times 0.03 divided by 4 equals. Now, when you do that, what number do you get? Can you read it to me? 90 exactly? Now, at that point, that's my interest for that first quarter. So I'm going to hit M+. So that's going to put that into memory. Then I recall memory, RCM or MRC, whatever you're going to have there. And you should, when you recall memory, see 12,090. Right? So that's my first time. And that's where you have to say, okay, I've done it once. Now, I'm going to take this and come back and multiply by 0.03 divided by 4 equals m plus. That's my second time. So you're going to do this loop here 11 times. And at the last, after 11 times, you're going to then hit memory recall. While you're doing that, I'm going to set it up in a different way. So I'm going to write something up here for myself. So what I've done is write the formula that we had on the front board. Okay, and I'm going to make some substitutions here, and I have 12,000 out in front. I have a 1 plus, and then it was a 0.03 over 4, and I had this for 6 years. Oh, that's my error. Ouch. 24 times, so you had to do 23 more times. Sorry about that. Small glitch there. So this is 24 times. So I'm going to leave this on the board. We'll just leave that up there. And it can be done, but by the time you've done 23 times, it's awfully hard to keep focused that long. Because at some point, you just sit there and you start thinking about anything else, and you go, am I 21, 22? And you go, and start over. So let's see what we should get doing it the way I have on the board. So I'm going to take the 0.03 and I'm going to divide by 4. So I'll take my 0.03, go to the screen here, divide by 4, hit an equal sign, and then I'll just add 1 to that. So this is giving me that 1 plus 0.03 over 4. That's going to be to the y to the x. And it doesn't help when you hit the square root key. Sorry about that. Come off there. I just managed to hit an incorrect key with the pen. I was not being careful enough. So let me try that again. 0.03 divided by 4 equals plus 1 equals, and now the y to the x key. And as I do that, I'm going to do that to the 24th power. Yes. And now I get this number. Let's see if I can slide it over so you can see it. 1. And then I have a 0.196413. So let me write that over here on the side board. And 1.196413. And there's what? Some more garbage after that? What are the next few digits? I thought, Michael, are you doing that on the calculator? Okay. So this is times 12,000. So that's what I'm going to do. Let's go back to the calculator. And I'm having to walk back and forth to the front of the room to the side board, hence the delay. But we're going to multiply times 12,000. So there's my multiplication, and 12,000 equals, and so I'm running $14,356. So let me write that in. And notice the comma's put at the top, which is sort of a strange place to locate it, but nonetheless it makes it easier to distinguish between that and a period. 35696. Okay, I'm rounding down to 96, so they rounded up to 97. Okay. And again, there are arguments in terms of the federal regulation regarding an annual percentage rate, and that makes sure that the bank gave you at least that rate. So 14,356.97. That you should be able to do with this looping, sliding over now, Ernie. If we'd gone through this, and I need to see the 23 there. If I'd done that, I would get the same answer if I kept track of things. But this is starting to get a little bit wild when you have to do 23 loops. Now, this is referred to as a do loop in computer jargon, where you repeat something like 23 times. We call that a do loop. and get the same answer. It's just using a y to the x key makes it so much nicer. And think of where you'd be before calculators on this. Okay, so if you go back, and as I've been doing, reading some of the information that's provided, you oftentimes find references to what we talk about. I'm going to get an eraser here and get something that reads a little bit better. I don't like the fact I've got the 12,000 looking so small there. 12,000 is a reasonable amount of money. But they do it with logarithms because that's the way things had to be done before calculators, so that you could do a lot of additions and subtractions. It was like adding exponents. Okay, so you wrote this number here as a power of 10. And you wrote this as a power of 10. So that's 1.2 times 10 to the fourth. This is going to be 1.19, but then the idea is you tried to write then just as a power of 10 for 12 and a 19, or 11. And the point out of all this is you were able, with logarithms, which were exponents, to add the exponents and do multiplication. So they had old-fashioned adding machines. The ones you pulled the crank down, they were called Marchand calculators. And they were very sophisticated. And they could even locate decimal points and so on. That's what banking had to deal with for decades. It wasn't until 1980s that you had banks across the board going to mainframe computers to do it. So that's the answer for, that was question number 5 in the homework. And again, just trying to deal with the questions. Kim?
How did you do that on the calculator again?
Okay, back to the calculator. Okay, just a minute. I'll do that again. A 12,000. What I did, and I'll show this up here as a kind of flow chart coming down. I took my .03, and I wanted to divide it by 4, correct? So I hit divide by 4. Then I hit an equal sign, add 1, and hit equals. And what that gives me is the part here inside. Now once I've done that, I hit the y to the x key. And whatever I have as an answer here is the base. So this is your base, this is your exponent. Then I have to enter the exponent, which was 24. So I hit the 24. Then I like to hit equals there, and that's where we should be seeing this number right here. This part of it. Then, when I multiply by 12,000 and hit the equal sign, I get this number here. Does that answer?
So this is the compound one on the calculator. This is the quarterly and semi?
Well, this is compound. We're still doing compound interest. Quarterly, semi-annual, annual, they're all compound.
But it's different on the calculator.
No. Look what we have here. I'm going to leave that on the board for a moment, and then I'm going to walk over here and look at what we did with this problem right here. So we go to the front board now. You'd have played the game the same way. You would have taken your .06, divided by 2, hit an equal sign, add 1, hit an equal sign, that's your y, hit the y to the x key, hit 2, equals, and multiply by 3,000, and get exactly the same process. Okay? Now that brings up an interesting question. Let's go back to the sideboard. What I think you're trying to deal with is something we talked about in Math 10, and I've done a lot more with it this semester. Continuous compounding. Okay? Now, we talk about daily compounding, and one of the comments I made to you is one approach to the interest on your credit card can be asking, if I take the amount of money you charged, and I compounded interest on that daily, how much would you owe at the end of the month? Okay, that is one way of doing the interest. So if I look at this same setup here, if I were doing this daily, what I want you to appreciate, you do exactly the same structure. But when you get down here to the y to the x, and we were doing this for what? 6 years. Okay, so this number, okay, is 0.03 over 365, and I'm supposed to do what? 365 times 6. So I have to find out what 365 times 6 is. I probably should do that before I start the problem. And then hit equals, and then multiply by the 12,000. Now that's what we call daily compounding. And that is if you had a balance of $12,000 in your credit card, and they instead wanted it for 30 days, then instead of taking this to this big number, you would have 30 over 365 instead of 4 times or 6 times 365. Yeah, where you do a fraction of a year, because that's the way interest is sometimes calculated for your credit card. Now, what is 6 times 365? Let's just compare this. 2190? Okay, so if you go ahead and carry this out, let's see what you get. Remember, before we had 14,356. This is the number we did compounding quarterly. Now we're doing daily. And what do we get this time, comparatively speaking? And again, with the EL 531, it makes it much nicer. What do you get?
1436.50.
Okay, now if we compare these two amounts, here you had 14,356. Here you have 14,366. We gained what? $10. Doing it daily over a 6-year period. Now that doesn't seem very impressive, but you only put in 12,000. But think of what's happening with the interest rates at 12% or 30%. And you're doing 12 million, not 12,000. Suddenly that 10 becomes $10,000 difference. And by the way, one of the things I was reading in the, had to be the Wall Street Journal last night. It doesn't come early enough for me to see it in the morning. And they were talking about in Ohio what they call short-term loans. This is when, a little bit like what Brazil's doing with the idea, you have 250% interest. I'll basically have a $400 limit, but I need $200 for the end of the month, so I use the credit card and pay it off in 2 weeks. Well, there are companies, at least in Ohio, this is where it was referenced, where you can go in and based on the fact your check's coming in 2 weeks, you can make a quick loan. And you'll do it like for 2 weeks. And the interest rates that they were running were 360%. Now, they don't tell you that interest rate. They just tell you for the 2 weeks you're going to pay this much. So I tell you, you're going to pay 7% for this per week. So a 7% per week interest. Well, there are 52 weeks in the year. So 7% times the 365, didn't say that right. Rephrase it. There are 52 weeks in the year, 365 days. 52 weeks, 7 times your 52 is getting up around that 360%. So they build in this idea that you think 7% is great. But I don't tell you it's for that 1 week. I just say 7%, and people think 7% is a great rate if it's an annual rate. So they tried to write legislation in Ohio this last period of time for the legislature so that the companies doing this, they're called stores, who are doing this would have to let you know that you're paying 360%. Well, they've managed to get around it in some way, and it's amazing that I did not realize in the United States we still had loan sharking at that level and that they're having trouble controlling it because they hide it in terms of fees, they hide it in terms of the language, and we are so susceptible. 7% is great. Geez, we pay 8.5%, we pay 8.375% for a state sales tax. 7% is less than that. Yeah, but that's an annual rate for sales tax, and that was a weekly rate, which morphs into 360%. Now, the next point. Banks don't just limit themselves to daily. They use a phrase, continuous compounding. And this is where I let things off in Math 10 last semester and have been pushing much harder this semester. Because we get to use the shampoo here. If you remember nothing else out of this unit, I hope you remember our green bottle of shampoo, PERT. Okay, where this again is your A, and this is P, E to the RT. Now the argument is, as I come back over, Ernie, now to this formula, here I have 1 plus 0.03 over 4, and then this was 4 times T. So this was actually 4 times T here. So the argument is, what happens as you keep compounding more often? So this denominator gets bigger and bigger and bigger. And then you go to that figure just for 1 year. So you would have this going to 1,000, this would go to 1,000. You get E to T. Well, in a sense, just E, let's see how I'll rephrase that, E to the R. So it'll be E to the R. You get E to the X in your calculator. And then if you do it for T years, you get E to the RT. And so that was a formula that came out of going all the way back, probably, I'm thinking in terms of time, certainly maybe 1800s in that period. And so if you take that idea, this parentheses here just becomes E to the RT. So if I do this problem, and I had an interest rate, and we said our interest rate on this problem was 3%, so I'm going to take my 12,000, and I'm going to take it E to the 0.03, and we said we'd do it for how many years? Was it 3 years? 6 years. That's all you do. It's that easy. So what is 0.03 times 6? It's 0.18, correct? So if you will hit E to the X key on the EL 531, hit E to the X. So if you do that, you'll have E to the 0.18. And you hit the equal sign and multiply by your 12,000. So the key is E to the X 0.18 equals times my 12,000. And this is your continuous compounding. And what do you get for that number? Okay, then you're doing something. You have E to the X key. What do you get? 14,366, 608, so we'd say 61. You get 11 more cents. Here was my amount compounding daily, and here is compounding continuously. Okay, so again, try your E to the X key. Okay, which calculator are you using? Okay, you've got the 20S. Okay, you have to be careful. With the 20S, I'm going to have to hit my 0.18 first, then hit E to the X. So for the HPs, hit your 0.18 and then E to the X, and then times 12,000. So it's going to depend a little bit on the calculator you're using. Does this work now? Okay? And we have a gain of 11 cents. Now, again, that is based on what? A very small amount of money as things go, 12,000. Well, what are the banks getting loaned under the TARP? You know, they're getting 12 billion. Not 12,000, not 12 million, but if you have 12 billion given to you, then the difference of this 11 cents is multiplied by, okay, this was thousands, so millions, billions, multiply that by a 1 with 6 zeros behind it, so that moves this over 2 places and has 4 more zeros after it. And so that's $110,000 difference from daily to continuous. So these small differences we're seeing don't seem much when you are talking small amounts of money. And that's very relative. $12,000 to me is a lot of money. You hand me a check for $12,000 and I'm real happy. Okay? Now, somebody in banking gets $12,000, they consider it pocket change because they're needing $12 billion. $12,000 doesn't do any good. Okay? So it makes a difference where you put your money. Big time if you have lots of money invested. Now, for most of us, I'd say think of the number of people who have $12,000 in the bank. I have a hunch in our economy right now, there aren't very many people who are going to sit there with $12,000 invested, and whether you get quarterly, you get annual, compounding, or daily, it doesn't make much difference as long as you're getting some compounding. Okay. Now, one of the things I came up with that really surprised me, and I want to play this back now in a different way. Let's take this same idea, continuous compounding. And by the way, you don't get this if you go to a savings. Let's see. If you go to a money market, CDs, things like that, you don't get continuous compounding. You typically get quarterly compounding. But let's say you had this continuous compounding and you wanted, at the end of 10 years, to have exactly $100 at the end of 10 years, and it was at a 10% interest. Okay, so my final amount, I don't want $14,000 at the end. I just want $100 at the end. At the end of 10 years, at 10%. Nice tens involved, right? So want $100 at end of. I've been doing too much work on a BlackBerry. Everything's column. You're coming down so I don't have to scroll. I want $100 at end of 10 years at 10%. Well, let's ask, how would you find the amount of money at the end of 10 years at 10%? Using the e to the x key, you would say that the x has to be what? Your 10 years times your 10%. Well, 10% is 0.1, right? And 10 times that is 1. So e to the first times some number is supposed to equal $100 at the end. Okay? Now, let's see if we've got this the way I want it. I want 10 years at 10% interest. So if I just did this much at the beginning, let's say you put $100 in, how much would you have at the end of 10 years? So you put $100 in, so you could say times e to the x, and then the people who have the e to the x key, and I'm doing this as a 1 here, and then equals, and what do you have? E to the 1 should be 2.718. So 27128. No. $271 and how much? 82 cents. Okay, again, you have 100 times. You hit your e to the x key, 1 equals. It should work that way. Now, if not, try doing this for me. Hit 1, e to the x times $100 equals. See if that makes a difference. You getting it or not? Okay? Now, my point is, how much, let's reverse this process. I don't want to know if you start with this, end with this. What happens if you want to end with this? How much money do you have to have at the beginning? So what we did, so you understand what we did here, we said 100 times e to the first, which was 2.71828, was how you got to this 271.82. Now, if I want this out here, okay, and I want some amount of money here that I don't know, times the 2.71828, because it's still, otherwise nothing changes here in terms of what e to the x is. Then I just divide 100 by what? The 2.728. So you do that for me. What do you get? No. You're going to take 100 divided by 2.71. $100 divided by E. No, it can't be 2 point. 100 divided by 2.78. Oh, I left a 1 off. My apologies there. 271828, but it's not going to change the number much. No? Divided by 2.71828 equals. There we go. $36 and thank you. Okay, does it make sense? It has to be up around $30, $40. This is called the present value. So you would have to invest right now $36.78 so that at the end of 10 years you would have $100. So $100 10 years down the line is the equivalent right now in our investment of 36.78. That's called its present value, working backwards, which is one of the problems you were doing in this set of problems. This is based on continuous compounding. We are having troubles with the calculator. Yeah. Okay? Okay, there's a way of doing it. But zeros are not bad. The extra digits are not bad. The 20S is a great calculator. Okay, now, I think there are more questions on 8.6, is my guess. And I'm a little bit at a problem here to the extent I really wanted to get into 9.2 today on graphing that we did in simple closed curves. And we are still having trouble just getting through some problems in 8.6. And Sarah's comment was 8.6 might be an abyss, and she was not willing to walk there. I'm now having questions whether I should have. But at the same time, since we did simple interest, this should be adding a little bit more to your understanding of simple interest. And folks, this is our economy. This is what we're dealing with right now. And the thing that, did I share yesterday what's happening on Bank of America with Visa? Okay. Where they went from like a 7% to a 29% for the APR on a regular credit card. And the person had paid their payments. This was on one of the news broadcasts in the last 48 hours. The person was making their payments more than the minimum, and they just sent a note from B of A on the Visa card saying, we are going to now charge you 29%. No late payments involved, just that's what they feel they need to survive. He called in protest. Well, you've got a very simple answer, my friend. Pay off your card and cancel it. But if you can't do that, then you're paying 29%. So this is like the AMRs that people were hassling. Let's say you owe $5,000 in your credit card. You were paying 7% per year. That's your APR, and it's now to 29. Your interest is 4 times what it was. So if you're making your same payments, you're paying less than you were before, and it's going to get paid off slower. Now, I think one of the arguments may be, this was then complained to at the federal level, and so it is likely that Congress will address whether the credit card companies should be hitting people over the head with the proverbial 2x6 with high interest rates. They won't spend as much money, and this, making it more difficult. And the argument is, look, B of A just got what? Huge amounts of money, and now they're hitting the consumer with all this extra TARP money they had, and that was the argument. So this sounds like a good time to stop this. So tomorrow I'm going to answer more questions on 8.6. Ernie, we've been listening to the police, which is what we should be calling probably with what's happening to the credit cards. But what is your choice as we close?